Hello. We introduce 6DOF head pose estimation through explicit bidirectional interaction with face geometry. In this study, we address the task of 6DOF head pose estimation from monocular images. Previous research on head pose estimation has primarily focused on head rotation estimation. In contrast, head translation estimation has received less attention. There are two main reasons why 6DOF head pose estimation from monocular images is challenging. 1. To estimate head translation, real-scale face geometry needs to be known. However, to determine real-scale face geometry, head translation must first be estimated. In other words, head translation estimation and real-scale face geometry estimation are strongly correlated. 2. Learning-based methods for head translation estimation suffer from severe generalization issues with out-of-distribution data. Unlike head rotation, the range of head translation is infinite, and strategies are required to address this. However, existing studies have not resolved these challenges. To address the aforementioned issues, we propose TRG. TRG utilizes the complementary characteristics between 6DOF head pose and face geometry through a bidirectional interaction structure. Specifically, TRG predicts both head pose and face landmarks simultaneously and iteratively updates the information between the two. We will describe the detailed structure in the proposed methods section. To reliably infer on out-of-distribution data, TRG does not directly estimate the head translation. Instead, it estimates a bounding box correction parameter. The bounding box correction parameter is combined with the head bounding box information and focal length to compute the head translation. We found that by inferring the bounding box correction parameter instead of the head translation, we could reduce the distribution gap between two different datasets. Due to this method of mitigating the distribution gap, TRG can perform stable inference even in cross-dataset evaluations. The feature extractor of TRG takes the image as input and generates feature maps. The feature sampler extracts feature vectors from these maps. The face regressor then infers face geometry and head pose from the feature vector. Additionally, the face regressor receives the head pose and face geometry from the previous iteration and outputs updated head pose and face geometry. The predicted face geometry and head pose are then projected back onto the image. At the resultant projected positions, feature vectors are re-extracted and fed back into the feature sampler. Since perspective projection is used for the projection process, face geometry and head translation become interdependent. To enable bidirectional interaction, TRG does not estimate face geometry and head pose all at once, but instead performs regression iteratively. Through the MLP layer of the face regressor, perspective projection, and feature sampling, the two pieces of information leverage each other throughout this process. Head translation is output by the face regressor. However, the face regressor does not directly predict head translation. Instead, it predicts the bounding box correction parameter. This bounding box correction parameter, along with the bounding box information, is used to calculate head translation. We assume that every person's head would fit tightly within a bounding box of size 0.2 meters by 0.2 meters, but this assumption does not hold in reality because head sizes vary across individuals. The correction parameter S is used to account for this discrepancy and serves to adjust the estimated head size accordingly. From the given diagram, we can establish the following proportion. After simplifying this proportion, we obtain the following equation. As a result, once the correction parameters are estimated, the head translation can be determined. We evaluated TRG's performance on the ARKit face dataset. The following tables demonstrate that TRG outperforms existing state-of-the-art models. Table 4 presents the evaluation results of TRG and existing state-of-the-art methods on the BUI dataset. Similarly, we can confirm that TRG outperforms the state-of-the-art methods. The following figure visually represents the head pose estimation performance of TRG compared to existing state-of-the-art models. The gray and gold colors represent the ground truth mesh and the mesh predicted by TRG, respectively. Other colors correspond to the meshes predicted by the existing state-of-the-art models. According to the figure, TRG's face prediction is the closest to the GT face. The next figure shows the face predicted by TRG, rendered in the camera space. Thank you for watching this video.